Topic of this video is parametric design for climate-responsive architecture, key concepts and frameworks. The contents of the training are: what is parametric design? Parametric design for climate-responsive architecture, climate-responsive goals, frameworks and tools, benefits and challenges, summary and reflections. The learning objectives of the training are: define parametric design and its relevance to climate-responsive architecture. Explore design logic, data inputs, and environmental goals. Understand how algorithms shape responsive and adaptive forms. Parametric design is fundamentally an approach that utilizes algorithmic thinking to solve design problems by translating the relationships between internal and external variables affecting design elements into parameters. In a parametric system, a simple equation defines and constrains the relationship between two or more parameters, meaning that altering one parameter automatically defines the others. For more complex systems, parametric equations are often mixed with algorithms, multi-step procedures that include conditions, loops, and restrictions used to control the values of multiple parameters. Parametric design is highly relevant to climate-responsive architecture because it transforms environmental criteria into quantifiable parameters that dynamically inform the design and optimization process. As climate-responsive design aims to achieve occupant comfort with little or no reliance on non-renewable energy sources by effectively incorporating local climate elements, parametric systems, based on algorithmic thinking and using data, variables, and their relationships, provide the necessary framework to study architectural conditions in a three-dimensional environment. The relevance is rooted in its ability to simultaneously manage the three conflicting basic factors: minimizing building energy demand, BED, maximizing indoor thermal comfort, DH, and minimizing building lifecycle cost, GC, through multi-objective optimization. The relationship between parametric design and climate-responsive goals is profound, as these tools allow architects to directly incorporate environmental performance targets, such as solar orientation, natural ventilation, and daylighting, into the creation of architectural forms. Parametric design acts as the mechanism for translating the complexities of climate strategies into dynamic, computable models. By treating solar orientation as a quantifiable parameter, designers can optimize building massing to regulate thermal comfort. For instance, in cold climates, algorithms suggest high solar absorbance for opaque elements to maximize heat gain, while in warmer climates, the workflow optimizes window U values and shading devices, such as tinted double glazing with a low solar heat gain coefficient, SHGC, to minimize unwanted radiation and glare. Furthermore, parametric design integrates natural ventilation as a crucial metric by facilitating optimal airflow through predictive modeling. Utilizing integrated simulation tools like Ladybug and Honeybee within Rhino, Grasshopper, architects can assess air circulation and energy demand to enhance passive cooling. In warm climates, optimal solutions often leverage materials with large heat capacity and night ventilation to release absorbed heat. These models are detailed enough to adjust individual cladding panels, even rotating them along an axis, to provide controlled air intake and exhaust, effectively incorporating specific aerodynamic requirements directly into the facade design. Finally, parametric design is essential for optimizing daylighting, which reduces energy consumption and improves occupant well-being. This process relies on multi-objective optimization, MU, to resolve conflicting objectives, such as maximizing natural light while minimizing the heat gain and glare that compromise thermal comfort. Modern approaches employ comprehensive evaluation systems that integrate indoor thermal comfort, discomfort hours, and total building energy demand, BED. By allowing designers to explore quantitative variations in geometry and window-to-wall ratios, WWR, parametric tools eliminate subjective assumptions and provide instant quantification of how design choices impact the quality of the internal environment. Parametric design is central to achieving climate-responsive goals, specifically minimizing thermal gain and maximizing comfort, because it provides the algorithmic framework necessary to analyze, simulate, and optimize these often conflicting objectives simultaneously. Minimizing thermal gain or reducing energy demand, which translates to lower cooling loads and overall building energy demand, BED, by allowing designers to treat building characteristics as dynamic variables subject to performance constraints. To achieve this, there are three ways: integration of passive strategies. Climate-responsive design integrates passive design strategies, such as shading devices, thermal mass, and insulation, to reduce energy consumption. Envelope optimization. The process defines the building envelope, the interface regulating thermal exchange, through a complex set of adjustable parameters. Parametric optimization searches for the most energy-efficient envelope properties. Data-driven decision-making. By integrating performance simulation, using tools like Ladybug and Honeybee, into the parametric platform, such as Rhino, Grasshopper, architects can quantitatively evaluate design schemes, eliminate subjective assumptions and making data-driven design decisions about how to best minimize heat infiltration. The maximization of occupant comfort is treated as an explicit objective function within the parametric optimization process, often measured by the reduction of the discomfort hours percentage, DH. There are 3 ways to measure this as well. Quantifying comfort as a variable. The International Standard ASHRAE 55 defines thermal comfort, and parametric research utilizes models like the PMV model to calculate the annual DH as an indicator for thermal environment comfort assessment. Night ventilation and thermal mass. In warmer climate zones, maximizing comfort often requires incorporating natural cooling cycles. The parametric optimal solution might recommend using high thermal mass materials which absorb heat during the day and release it at night, allowing the heat to be taken out of the room through night ventilation. Multi-objective optimization, MU. The essential relationship lies in the unavoidable conflict among design goals. Making the indoor thermal environment highly comfortable usually leads to an increase in building energy consumption, bed, and life cycle costs, GC. Parametric design leverages MU algorithms, such as SPIA2, to manage these trade-offs. The relationship between parametric design and climate-responsive goals is that parametric tools provide a rigorous, quantifiable, and visual framework for incorporating these critical environmental factors directly into the architectural design and optimization process. Parametric design enables architects to translate complex environmental data and performance requirements into parameters that dynamically shape the design solution. Rainwater harvesting is a key strategy within climate-responsive design, promoting effective water management and conservation. Parametric design facilitates this by integrating the technical requirements of stormwater management directly into the site planning process. Quantitative dimensioning. Parametric tools automatically calculate and visualize 3D detention ponds, ensuring sufficient storage during heavy rainfall to prevent hydraulic system flooding by linking site geometry directly to critical stormwater volume requirements. Defining critical parameters. The required storage volume of a detention pond is determined by several parameters, which are transferred into the parametric model. Integrated design workflow. By merging architectural site design with the hard criteria of stormwater management, parametric tools allow designers to instantly evaluate changes against the quantitative design requirements. This semi-automatic approach provides instant visual and numeric feedback, allowing designers to make more informed decisions about the location and size of water management features early in the design process. Shading devices are a fundamental passive design strategy used to reduce solar heat gain and glare, thereby enhancing building performance and occupant comfort. Parametric design enables the precise control and optimization of shading elements, controlling geometry and performance. Parametric tools allow the geometric definition of complex shading elements, such as overhangs and louvers, to be directly linked to performance requirements. Ventilation and aesthetics. Parametric models can define the functional and aesthetic aspects of shading simultaneously. Iterative refinement. An abstracted elevation was created in a spreadsheet where each cell represented a panel, and its potential for rotation and resulting vented area and wind exposure were calculated. Ecological integration refers to blending the built environment with natural systems to foster sustainability and resilience. Parametric design enables the modeling and integration of biophilic design elements and green infrastructure, green roofs and walls. Climate-responsive design incorporates green roofs, living walls, and vegetated surfaces to enhance insulation, absorb rainwater, reduce the urban heat island effect, and promote biodiversity. Modeling biophilic structures. Parametric tools are essential for managing the complexity of these designs, where extensive vegetation on balconies creates a microclimate, reduces heat absorption, improves air quality, and supports biodiversity. Promoting biodiversity and ecosystem services. Environmental ethics in architecture, supported by climate-responsive design, advocates for features like green roofs and vegetated facades that support biodiversity, ecosystem services, and urban wildlife conservation. The application of parametric design relies heavily on digital frameworks that define complex geometric relationships and automate performance simulations. The Rhino Grasshopper platform is the industry standard for this research. While Rhino provides the 3D environment where all entities begin as coordinates in space, Grasshopper serves as a visual programming package that integrates performance plugins and evolutionary solvers into the modeling process. The optimization workflow begins with parametric model creation, where building variables are input into the Rhino Grasshopper platform to generate a dynamic geometry. This is followed by iterative simulation, utilizing environmental plugins like Ladybug and Honeybee to conduct detailed analyses of the building's energy demand and internal environment. The process then moves to optimization and Pareto solution search. Resulting data is fed into evolutionary solvers like Octopus, which utilizes the SPIA2 algorithm to identify the Pareto frontier. This frontier represents a set of non-dominated solutions that balance conflicting objectives, such as minimizing cost while maximizing thermal comfort. Finally, the results undergo data visualization in software like Excel or MATLAB, allowing designers to interpret complex trade-offs and make informed, data-driven decisions early in the design phase. The relationship between Dynamo and Revit concerns the integration of parametric thinking into building information modeling (BIM) platforms. Revit is a BIM software platform widely used in the construction industry. While its internal parametric equations were often hidden behind the user interface, scripting interfaces made parametric modeling possible. Dynamo is the visual programming package used as a widely used open-source plugin for Revit users, which extends the platform's parametric functions. Dynamo can even embed Python scripts to define new programming functions. Both Grasshopper, Rhino, and Dynamo, Revit fit within the broader need for interoperable, automated design workflows in the architecture, engineering, and construction (AEC) industry. BIM platforms. These tools support building information model (BIM) platforms, which link variables, dimensions, and materials to geometry. This means that when an input or simulation value changes, the 3D model automatically updates all lifecycle scenarios and components simultaneously. Automated solutions. The automation provided by these tools is crucial for climate-responsive design, as it allows architects to create visually compelling forms that are also environmentally sensitive. By utilizing digital tools and methods, designers can develop expertise to engage creatively in design, moving beyond using the tools solely for visualizations or after designs are completed. Plug-in limitations. Although these platforms allow for free plug-ins for various CAD tools, including Grasshopper, Revit, and Rhino, a major issue is the inconsistency in non-compatible format exchange between different platform applications. Ladybug and Honeybee are essential environment analysis plugins used in computational design workflows. Their primary role is to bridge the parametric geometric model with rigorous climate and energy simulations necessary for climate-responsive optimization. Integration with parametric platforms. These plugins operate within the popular Rhino Grasshopper parametric platform. This integration creates an efficient workflow where design changes defined parametrically in Grasshopper can be immediately analyzed environmentally. Simulation and analysis capabilities. Ladybug and Honeybee conduct modeling analysis of the building environment and energy demand. This environmental analysis is the iterative simulation stage within the multi-objective optimization process. This capacity enables designers to transition research from qualitative analysis to energy consumption simulation based on quantitative research. Role in optimization workflow. Once the building parameters are defined in Rhino Grasshopper, the workflow proceeds through the following steps. Parametric model creation. Building parameters are input into the Rhino plus Grasshopper platform to generate the parametric model. Iterative simulation. This model undergoes iterative simulations using Ladybug and Honeybee. Pareto solution search. The simulation results are then fed into optimization engines, like Octopus or TT Toolbox, to search for Pareto non-dominated solutions that represent the best trade-offs between conflicting objectives, such as energy demand, cost, and comfort. In essence, Ladybug and Honeybee allow the parametric framework to analyze how variations in design elements, such as orientation, window type, or insulation thickness, directly impact climate-responsive performance metrics before the design is finalized. The parametric design frameworks integrate various environmental and material factors as key parameters to drive the form and performance of a structure, ensuring it is highly responsive to real-world conditions. These factors, such as sun path, radiation, wind flow, and material response, are essential inputs that define the constraints and objectives of the optimization process. In parametric design, sun path and solar radiation are treated as critical scenario variables that inform the geometry and material choices of the building envelope. Site analysis and orientation. Climate-responsive design relies on analyzing local climate data, such as sun paths and topography, to determine the optimal placement and orientation of buildings. The primary goal is solar orientation, which means orienting buildings to optimize solar gain in winter and minimize heat gain in summer. Radiation and optimization. Parametric modeling treats building orientation as a parameter that is varied to achieve optimization goals. The best building orientation is consistently the east-west orientation to facilitate the maximum use of solar radiation in colder seasons. Solar absorbance. The sources treat the solar absorbance of the external wall and the solar absorbance of the roof as crucial design parameters. Parametric optimization reveals that the solar absorbance of the roof and external wall generally increases from warmer climate zones to colder climate zones to maximize the utilization of solar radiation. Window performance. The solar heat gain coefficient, SHGC, of windows is a critical parameter. Parametric analysis recommends selecting windows, such as tinted double-glazed units, with a low SHGC value to effectively reduce excessive solar radiation entering the room in warmer climates. Wind flow patterns are vital parameters for implementing passive design strategies like natural ventilation, which helps regulate indoor temperatures and air quality. Wind analysis and ventilation. Site analysis involves understanding wind patterns to design for natural ventilation, thereby reducing reliance on mechanical HVAC systems. Passive design strategies specifically include designing for cross-ventilation and the stack effect to facilitate airflow. Air change rate. Parametric models incorporate an air change rate, infiltration and natural ventilation, defined as a parameter, e.g., 0.8 volume per hour, that affects thermal performance. Integrated solutions. Parametric design can model complex relationships involving airflow. For example, in the design of the Lansdowne Road Stadium, the parametric model defined a third axis of rotation along the long axis of the cladding panels, allowing them to rotate between 0-ring operator, closed, and 90-ring operator, open. This rotation was incorporated parametrically to provide air intake and exhaust for air handling units, illustrating how wind flow requirements can influence the facade geometry. Material response refers primarily to the thermal characteristics of building components, insulation, mass, conductivity, and their ability to regulate temperature, which is directly parameterized in the model. Thermal mass and insulation. Parametric design treats material properties, such as the insulation thickness of external walls, roofs, and ground floors, as decision variables to be optimized. The concept of thermal mass, incorporating materials like concrete or brick to absorb and store heat, stabilizing indoor temperatures, is a central passive strategy. Optimization by climate zone. The optimal material choices are determined by the climate parameters, which are warm climates and cold climates parameters. The optimization process also considers the block thermal conductivity and block density of the construction materials, as these factors, along with block thickness, determine the U value and overall thermal performance of the envelope. Parametric design transforms traditional architectural intuition into data-driven, environmentally focused workflows. Its primary benefit lies in enabling quantitative analysis and optimization, where tools like Ladybug and Honeybee simulate building behavior and environmental conditions. This supports objective decision-making and reverse search optimization, allowing designers to start with performance goals and work backward to identify ideal design parameters. Another advantage is multi-objective optimization, MU, which is essential for balancing conflicting goals like energy demand, thermal comfort, and cost. Using algorithms like SPIA2, designers can explore Pareto optimal solutions that reveal necessary trade-offs and offer stakeholder-specific scenarios, such as cost-optimal or maximum comfort designs. Furthermore, parametric design enhances the early integration of technical criteria. It consolidates architectural, engineering, and environmental considerations, such as stormwater management, into unified models, enabling automatic calculations and rule-based geometry that reflect real-world constraints. Finally, these tools support innovation in form and aesthetics, enabling designs that are visually expressive yet environmentally responsive. By embedding climatic data into form generation, Parametric workflows foster resilient structures capable of responding to climate risks, strengthening both technical rigor and creative potential. Parametric design faces significant conceptual, technical, and educational challenges. Conceptually, it is often confused with parametricism, which prioritizes algorithmic aesthetics over environmental performance, potentially overshadowing sustainability. Technically, interoperability issues between BIM platforms and simulation engines like Energy Plus hinder workflow and knowledge transfer. Furthermore, complex environmental variables, such as stormwater management, remain difficult to automate due to their interdependent nature. Educationally, a gap exists where students struggle to integrate digital skills with theoretical depth, leading to shallow exploration. This disconnect prevents the meaningful application of parametric tools in creating truly climate-responsive architecture. Parametric design for climate-responsive architecture employs algorithmic thinking to solve design challenges by translating the relationships between external environmental variables, such as local climate elements, and internal design requirements into defined parameters. This approach generates parametric digital models where entities automatically respond to variations of input data, allowing the system to be developed and evaluated in a three-dimensional environment. Using platforms like Rhino, Grasshopper integrated with environmental analysis plugins such as Ladybug and Honeybee, architects conduct iterative simulations to quantitatively analyze the building environment and energy demand. The primary goal is multi-objective optimization, which iteratively searches for the best design parameters, e.g., orientation, insulation thickness, solar absorbance, to simultaneously maximize indoor thermal environment comfort, DH, while minimizing building energy demand, BED, and building lifecycle global cost, GC. This capability allows architects to make data-driven design decisions and create structures that are both visually compelling and environmentally sensitive.